started. This is the last session planned for the chapter 3 of sheep theory through examples. That chapter focuses on universal constructions and these constructions categorically that have universal properties and can be applied to vast arrays of categories. So they're not necessarily all categories. So we've been looking at products and coproducts, equalizers and co-equalizers, and terminal and initial objects of those successive pairs. The first set have all been limits, the second set co-limits. And then today, last time we talked about pullbacks, another example of a limit, and today we're going to be talking about pushouts. And like pullbacks, pushouts are somewhat more, Eugenia Cheng's words for them are more advanced, somewhat slightly more elaborate constructions, but they're extremely useful constructions. One thing that I'm hoping to touch on at the end of today's session is just kind of a recap in some themes that you see cut through limits on the one hand, or cut separately through co-limits on the other, and kind of unite them. They have similar flavors. And we'll see if we can get to that today. But first, let's jump into pushouts. And like last time, a lot of my material today is going to be drawing on Eugenia Cheng's work, in particular her chapter 19 from Joy of Abstraction, as well as this material in chapter 3 of sheep theory through examples. Okay, so we had talked about pullbacks, and I'd like to talk about pushouts. I had noted just now that 3 of the types of constructions we've looked at are limits, and that the other 3 are co-limits. Not all universal constructions are limits, or are either limits or co-limits. For example, the exponential object is not. But the ones that we're surveying in the discussion of this chapter of sheep theory through examples are. And co-limits here for this chapter include initial objects, coproducts, and pushouts. And we had discussed a little bit, kind of gestured at some of the definition of limit as introduced in chapter 3 of this book of sheep theory through examples, with this idea of a cone and capturing cones through functors from diagrams, including a constant functor and a functor from a certain shape, which varies by universal construction, but for coproducts or pushouts, or indeed for initial objects. I'm not going to go in as much detail here. I'll simply say that a co-limit over a category is the same thing as a limit over the opposite of that category. So they're just dual to it. And amongst other things, with a cone, you may remember, I should really have had a nice little diagram. You may remember this idea of a cone, which is involved in the limit construction, where we have one diagram selected by a shape, with different shapes being associated with different limits. And we have cones over it, right? Such that these triangles have to commute. All these different components down have to commute. But now we're going to be dealing with co-cones. So we're dealing with the opposite of a category. We're finding a shape in the opposite of a category. And by implication, these limits will go to the co-cone, the apex of the co-cone. But like before, we'll have universal properties where we have unique factorization through the universal property for anything else that has its likeness. Anything else that has a similar cocone will be factorized through the universal cocone. The one with the universal property associated with it says that there's unique morphism to anything else like it in the diagram, that it serves this kind of unique mediating role in the category. I'm just showing it for cones here, but you can imagine things with the arrows just turned around, and you'd get cocones. And they're the universal, the morphism, unique morphism associated with universal property would go up. Okay, so that was a little bit about colimits and pushouts. I'd like to dive now into the specific of pushouts. So here, as before, we have a shape associated with this construction, and that shape involves something like this, and we're going to find this in the opposite of the category. So we'll be finding things where we have a morphism into C and a morphism into B, into C from A and from B. Okay, so we're looking for a certain shape in category op, and we'll find it in a situation like this, and this will be our object associated with the universal mediating property. This one here, this might be what we call informally the pushout, but it's really this whole construction. And we talk about it being a pushout over C, pushout of A and B over C. Now, this should seem at once familiar, but slightly disorienting, because for a pullback, you may remember the object with this universal mediating property was up here in the upper left, right? And we had morphisms out of it. Here, it's the one in the lower right, and we have the morphisms into it. And this is the thing at the apex of the cocone. So all these things, A, B, and C, have morphisms to it. We just don't draw them here. But there's a unique one here that's at once the composition of this and of this. Hence, this is a commuting square. So this is going to be the pushout of A and B over C. And we'll talk about what that means in just a minute, because what it means to be over it is a bit different from with pullback and its particulars. So once again, this is going to meet the universal property. So for anything else, any other square of this sort, like this one involving x, it's a square, even though we're drawing it geometrically as something different than a square. It's a commuting square. See, T and then G is the same as S and F for this contender X. But we want the best of them, the most essential of them, the most minimal of them, the most quintessential one. We want the V, the pushout. And what distinguishes that is that for anything else that's similar, any other pretender to this throne, there's unique morphism from this one to this contender, such that these squares commute, such that Q and then K is the same as P and then K, and moreover, Q and then K is the same as G. Excuse me, I said that wrong. Excuse me. I said Q and then K is the same as P and then K. Excuse me. It's Q and then K is the same as G. P and then K is the same as F. Are we okay with this? Okay. So this is the unique mediating one. This is the one that's the best representation of something that has these properties of having a commuting square like this. Now, as you'll see, this looks maybe a little bit, you might say, well, thank you very much. Okay, I'll trust it, but there's wonderful utility to this, and we'll get to this. Having this universal property gives us this incredibly versatile gadget that we can use that has wonderful properties in practice. Okay, so we're going to draw it like this, and there's this little indicator that shows where the pushout is. But you can always find it because it's the one here that these go to. But actually, to distinguish this if this is drawn in another orientation, you want to be clear this isn't like a pushout square. It's a pullback square, and this little thing will excuse me, it's a pushout square, not a pullback square, and this little thing will indicate that. Okay, so let's talk about the intuitions for this, if we could. The intuitions for pushouts are wonderfully rich and wonderfully useful to apply, and it reflects the fact that the pushout itself is wonderfully rich and useful. So here are the rules I'd like you to keep in mind. The single best one I find, the single most useful, is that a pushout of A and B over C is a gluing together of A and B around C. In other words, C glues them together. As we'll see, if C is the terminal object, this will just be A next to B. In other words, the what of A and B. Just what universal construction is just like A next to B, the coproduct. So if this is the initial object, if I didn't say initial, if I said terminal, I meant initial. If this is the initial object, this is just A next to B. These are just the unique morphisms here, and there's nothing to glue around. Think of this as like the empty set, if these were sets. There's nothing to glue around. The set around which we glue A and B is empty, if these were set. But it's much more general than set. C is some commonly like a subpiece of A and B, or has some place in A and B as found by S and T. And we're going to glue A and B around the things identified by C, by a single component C. So we're going to stick A and B not just next to each other, they're going to be basically next to each other, but they're going to be glued together around C. That's one way to understand it. And that's actually my go-to way. But there's another way too, which is actually really useful. And I want to show you that too. We could think of the pushout as being A, undergoing the same homomorphism seen in this mapping here, or a similar homomorphism. So C going to B does something to the C inside that is reflected in A through S. And what we're going to do here is take A and sort of apply a similar operation to it that we see here. We're going to take A and apply this sort of operation. Alternatively, and just as well, this is symmetric, you could consider it as taking B and applying the same operation that we undergo when we go from C to A. Okay, so C to A does something. It like finds C in A, for example, and we're going to take B. And we're going to basically go and give it context, give B context that that C gets an A. We're going to be adding things in from A to B. This way, it's like adding things in from B to A, but keeping them together around the things that are from C. Okay, so that's kind of abstract. Let's see some examples. You'll find it's very familiar and it can really grow on you. Okay, so here's our pullback square. We're going to be looking for the pullback down here. These are the raw materials we're dealt. This is our A, and this is our B. And what I've indicated in each of them, and this is our C, but I've indicated in each of these where the single item in C maps to. So if this is a graph, so this is a graph homomorphism. This morphism is a graph homomorphism. It's finding, as it were, this graph in this one with possible squishing down occurring, right? So we're finding, so T is finding this here in this graph. It's finding this in this graph. And what we're doing is with the pullback, or excuse me, the pushout, we're taking A and we're taking B and putting them next to each other, but we're gluing them around the image of C in each. So C mapped to here for B, it mapped to here for A, and we're sticking this together with this with just a single vertex for what's come from C. So this is what we get out. You can kind of see the B part of it. That's this one. You can kind of see the A part of it. That's this one here. And they're glued together. They're stuck together around this common place that's the image of C. Do you see that? So like what C went to, we're gluing them together around. Okay. Okay, let's take this. Let's reflect on the fact that C might not just be a single vertex. It might be something more complex, right? Okay. So suppose C were this edge. So here we have two vertices and one edge between them. Now suppose B is this construct. This is another graph, right? Sorry. B. So it has two edges end to end. And you'll notice that I've shown in red where C maps to here, right? C maps to something here. Are we good with that? C maps to this. In B, C maps to this in A. So this is A. Oops, sorry. This is A here. And C maps to this portion of A. And so we're going to stick A and B together, not as solitudes, but glued together around this common point. This common point will be merged, will be fused between them. It's not a point. This common subcomponent will be fused, will be merged, will be identified is another term we use. It will be viewed as the same between them. So what do we get? Well, we get this next to this, but they're fused around this first part. So we get this, and then we get a little thing sticking out of it, and then we get this other thing sticking out. So we get this. Do you see where that came from? This component came from here. From here. This component came from here, and this came from both, right? But not as solitudes, but they're the one and the same. We've identified, so we're taking A and B, identifying the image of C in each. Yes.
Oh, question.
Yes.
When not B and A, the common pattern is lateral pattern.
So, say this again.
Like C, why B and A's common pattern with C are the first part rather than the
second part?
second part.
Oh, because great question. Yeah.
That
Yes.
that every vertex of itself.
That's true. So I think you're saying like, well, why is this? So this is an example, but like, why is it that this mapped to the first part? Like, why didn't it map to this, or why didn't it map to this, or in fact, why didn't it just collapse this down to be this arrow? And those would be different homomorphisms. I'm showing you, great question. I'm showing you one particular homomorphism here where T maps this to this. That's, in other words, what I'm showing you here is for a specific T, the one which maps this to the first part here, for a specific S, where it maps this to this one here. And I'm showing the push out over that of A and B over C, given this homomorphism. Now, I think the deeper question you may be asking, which is a good one, and I think Eugenia Cheng may actually comment on this, is it's a little bit glib. It's a little bit oversimplified to say it's A and B sort of over C, because it's actually not just C, it's the mapping from C to B that matters. And the mapping from C to S that matters, the specific mapping. Maybe this is a good chance to actually do a little example where if it was a different mapping, right? So let's take this to the board and let's go and imagine that.
Yes, because I remember in CalLab, we
Yeah.
apply graph homomorphism, it's not like unique.
It's not unique.
It's
Yeah.
not unique.
Yeah, that's right. You can ask homomorphisms and we'll give them back to you, the whole set. Okay. So let's go do a similar thing here. So what we're going to have, and I know this isn't displaying right now, just for my characterization. Maybe I will draw it like this. So this is going to be our edge, right? These are graphs. These are C-sets from the graph schema. Remember that? Each of these is a graph. And we're looking at graph homomorphism. Thank you. That'll be really handy. Okay, so I'm drawing our pushout square, right?
Yeah.
Where's our pushout live in the square? Where does it live? Bottom right. Yeah. So we're trying to figure out what this is. And what I'm going to say is this one up here, I shouldn't have drawn it so tight. We're going to, instead of having it draw it to the first one, we're going to draw it. This has two in a row.
Yeah.
And I'm going to have it map. Maybe what I'll do is, can I do it on top of this, Yuja? Or would you prefer me to not sully it with the red?
I don't know, doesn't matter.
Okay.
Yeah.
Something like that. And it's gonna go to this one here. Are we okay with that? Okay. And meanwhile, for this one down here, maybe we'll keep this one the same, and then we'll iterate it. Okay, so this one will be like this. And this is the image of C. This is, we'll call this C. Right? This is A, this is B, and this will be our push out, right? D. Yeah, good. Okay. So we have this being in the image of C. In other words, when we take the graph homomorphism, it goes there, goes here, it finds this shape here, right? And then we have what? We have one more, and we have a self arrow here, right? Okay. And then the question is, what is this going to be? What will this look like? You tell me. What will it look like? We're going to take these two things, we're going to glue them together around the image of C. So what will it look like?
Three vertices and one was.
Three
The third
vertices
one has
in a
a
row.
And
Or 3 arrows in a row, actually, right?
3 arrows in a row.
Yeah, 3 arrows, yeah.
And then the last
Good. Well, where does the first arrow, whence does the first arrow come? Where does it come from?
From B, right?
Far left.
Yes, yes. Jeff maybe the person here knows whence. It comes from here. It's an old English word. Here, Chaucer would have used it. So this comes from here. Where's the second arrow come from? Both of these. And then where does the last arrow come from? Yeah. A. Okay. So it's like
Oh,
this one is from here. Then we have, I'm gonna, forgive me for drawing it, but I'm gonna draw it like this. It's the one that was picked out by
it is C.
yeah. I think it's true, like if you go like that and then you follow it through. Yeah. And then there's another one from this, and then what are we still missing?
The self arrow.
The self arrow. Yeah. We comfortable with that? Okay, so that would be a different homomorphism, perfectly valid. But what I was saying is that it's a little bit glib to say that this is just over C. It's actually over this map from C to A and B, right? That's what it's over here. Okay. But meanwhile, these maps, by the way, are just like they are just like injection homomorph, or they're like a straightforward homomorphism that you don't have to specify. It's not like you have to specify these, but you will have to specify these generally. And in CATLAB, you will have to pick one. Okay, do you want to do another one here? Like, do you want to do another one around this? Okay.
I'm getting the vibe that it feels very analogous to the pushout is the union of A and B over C, and C is the intersection
Right.
of them.
Right. It's like identifying these. You should be, you might be reminded slightly also of the co-equalizer, where we like put some things in the same equivalence class, like these are considered in the same equivalence class. Like the co-equalizer would take what's in A, what's in or what's in the two things, but then it would identify the ones that are mapped to by a given element of X. And this is kind of very much, we identified these, we fused them. Okay, so okay, maybe I'll use one of the other rules though here. You can also think of this. My argument was it's very useful to think of it as gluing these structures together around the common point as mapped to by C. But another extremely useful way is to think of this as like doing to A what this mapping does to B. What does this map, does to C? So this mapping up here from C to B, what is it kind of doing to this? It sticks an arrow in before it, right? That's what it does. It kind of sticks an arrow. So that's what happens when we go from A to the push out. We stick an arrow in front of this, right? That's what's happened. Stuck an arrow right in front of it. We've kind of undertaken the transformation here and applied it here, bearing in mind what C maps to here. So it stuck an arrow before the image of C. It's sticking an arrow before the image of C here. Okay, but we can apply this the other way too. We can ask, what is this doing? Well, it's sticking an edge in it with a self arrow at its end here, right? And that's what's going on here. We're taking B and we're taking this component that was mapped to by C, and sticking an edge with a self arrow on it. Do you see that? So that was the point of my other two, my other two sort of ways of thinking about this, which I think I got from John Baez. But it's this thing. In this mapping, A undergoes the same sort of homomorphism or similar homomorphism seen here, bearing in mind what C maps to an A. Or B undergoes a similar homomorphism seen here, bearing in mind what C is mapped to in B. So that was my point. Okay, should we do another one here? Okay, so maybe I'll draw it up here. So here we're going to have our C. Maybe I'll just draw it here in blue. And what should we have it mapped to now? What's your pleasure? Where do you prefer? What should this map to? Like, do you want it to map to something, I guess something different here, maybe? Like map to this guy or map to the self arrow? Should we do it to the self arrow? Okay, cool. So this will be C. We do it in blue. All right. This will be A. We're gonna have two arrows in a row. And then we're gonna have blue like that. And this will be B. It'll just be two arrow. Oh, sorry. Which one should we do? Should we do it as the first one or the second? Which do you prefer? You want to do it as the second one, just so there's only one change here for what's shown on the board? The first one is what we showed earlier. Okay. Okay, so we're gonna compute the push out here of these graphs, right? And of these graph homomorphisms. Okay. Okay, cool. So what is this going to look like? Can you tell me? This is actually really interesting. What's that?
Three vertices.
Three vertices. Okay. Okay, so
And
another vertex. Yep. Yeah. Oh, okay. Okay. So sorry.
another vertices.
Okay, I'm going to, just so that we're clear about where these come from, I'm gonna call these arrows, I could call them E something, but maybe I'll just call them X, Y, Z. Is that okay with you? Okay, so which one is this coming from?
X.
X. How about this one?
Y.
Y. Okay. Okay, and then where's this guy going? Where is this guy going?
Another vertices that's connect this versus to last.
Like this. And then where's the blue?
Some white with some.
I don't know. Okay, so you can see actually some of the value in thinking flexibly about this, because it can seem weird to like, how do I identify a self arrow with this? Like it's not so clear. But if you think about this as doing something here, it like folds up this thing. You could think of this as like folding this one up. It's acting on this in a way that folds it up and puts two arrows in front of it, right? Two arrows right in front of it. Boom, boom. That's what's happening. It's like taking this, folding up So this gets folded up, but two arrows get put in front of it, and that's what we're doing here. Alternatively, just as well, you take this and you identify, you do to this what this is, which is basically stick an arrow onto the front of where this blue thing comes from, whence it comes. Right? It sort of stuck an arrow whence it comes, from which it's come to this vertex. So it sticks. That's what this is, this is doing. It's sticking this arrow in front of this, of wherever this is. This here is here, so we stick an arrow onto that, right? So that's a useful way to think about it when the gluing intuition runs into trouble. So that's kind of fun. The amazing thing, though, is as a pushout, if something that has these universal properties, it could apply to a vast range of categories and critically to all C sets. So we could do this for causal loop diagrams, right? We can identify things with causal loop diagrams and have similar flavor of this. Okay, so do you want to go back to another example of slides, or do you want to do a different one? Like with a causal loop or with another graph, or what? What's your preference? Okay, not hearing something. Maybe we'll continue on the slides for now. I want to get to discrete dynamical systems. This will be another fun push-out example. Okay, so we'll go here. I'm watching the time. Okay, there we go. Come on. Why isn't this sharing? Okay. So I think you're getting the flavor of it and the utility of these rules. Okay. So here's a challenge. Challenge. Okay, so maybe we did this one. Oh, no, we didn't do this one. Oh, yes, we did. We did. We did. Yeah. There we go. Okay. Okay, but as I said, this can be applied to any C set. Bunch of those bouquets, we saw in chief theory through examples for graphs, for reflexive graphs, for symmetric reflexive graphs, for causal loop diagrams, for stock flow diagrams, for Petri nets, and for discrete dynamical systems, for example. So here's our discrete dynamical system. Do you remember what this was? Just to make sure people are on board with this being a C set. What was the schema category for discrete dynamical system? Do you remember? Remember what was the schema for them? So I'm saying this is a C set. This can be encoded as a C set. What is C? It's a mono. It's a free monoid. So in other words, single object. That's what maps over to the set of states. And then a single morphism that is in the single generating morphism, but basically it's free. So whenever you compose it with itself, it's a new morphism subject to associativity and so on, and unitality. And so that's associated with the natural numbers. It's the monoid of the natural numbers in plus encoded categorically, right? Okay, so that schema, single object, single generating morphism, but it can be iterated and get any number of distinct iterations. If we map that into set or fin set, we get a set of states in a next morphism. Do you remember that? We had it up on the board long ago. Remember that? We're dealing with homomorphisms between these things. Remember that? Okay. So we could draw these in the category of elements like this. I'm drawing actually in the category of elements like this is one. This is another. How many states does this dynamical system have? 3 states. This state, and this state. Call this state 1. Where do we, and call this state 2, this state 3. Where do we go after state 1? State 1 goes to what? When you do next on state 1, you go to 2. When you go to 2, you go to 3. And after 3, what happens when you are in 3? What's the next state after 3? No, yeah, 3 from now on. Okay. So I'm saying this is do you agree this is a discrete dynamical system? Well, it's two states going one to the next, and then third, which is just an entrapping state, right? How about this one here? How many states does this have? 4 states. 1, 2, 3, 4. Are we okay with that? Okay, I'm going to take the push out of these C sets. I'm going to take the push out over these discrete dynamical systems. What is the discrete dynamical system I get? Well, let me ask, let's think about it. Put aside push out for a moment. What if I took the coproduct over these? What would I have? They just be next to each other, right? It'd be like one dynamical system next to the other with there'd be solitudes, there'd be no interaction. Do you agree with that? Okay. But if I take the push out, what do we see? What is it? When we take the push out of these over this, in other words, take into account this, that this maps to here in A, this C maps to here in B. What are we taking the push out over? Or sorry, what's the results of that push out? How many states will there be in the resulting dynamical system? 6 states. 1, 2, 3, 4, 5, and 6 is the same between these two. It's identified. We've glued it around these points. Is that okay? We glued it around these points? Okay. And so we get this dynamical system with 6 states. You could call this state 1, 2, 3, 4, 5, 6. If you start in 5, you go 6, and then 4, 4, 4, 4, 4, 4. If you start in 1, you go 2, 3, 4, 4, 4, 4, 4. If you start in state 3, you go 3, 4, 4, 4, 4, 4, right? This is a dynamical system, right? Okay. Okay, so is there something that disconcerts you slightly with this? Okay, let me ask this. Let's suppose that we identified state 1 here with state 1 here. So suppose, I'm just curious, it's a thought experiment. I actually haven't thought this through, although I have my intuitions for what will happen. Suppose we went like this. suppose we went like. We identified that with this. And I'm asking you, what's going to happen? So this finds this pattern here. I guess technically,
Yeah. The state in B doesn't have a self next arrow.
yeah, so. Okay, so let's think this through. This needs to map. So this needs to be a homomorphism, right? So it needs to be the case that if we start here and so this needs to be actually it's a natural transformation between C sets is what it is. I mean, this is how we draw it diagrammatically, but this is not a morphism in a category. This is just a diagrammatic representation of the dynamical system. So if we had this needs to be natural transformation, right? It needs to be the case that right. Okay. So let's think about this as I'm actually quite puzzled by this. This is a puzzle. I have my guess as to what will happen, but let's think this thing through. Okay. So what we want is we have two C sets here. And we drew them as dynamical systems. Right. We drew them as dynamical systems. I'll draw one as a dynamical system, this guy here. And what I'm saying is we're trying to say that this is a homomorphism of dynamical systems like this, that this goes into this. And so this goes to, I think Jeff has the key intuition. I think actually this needs to be a homomorphism into something right. If we can map this, we could say it's this, but then the source of this, we're going to have to identify what this is, right? That's the key thing, what this goes to. And if we say this goes to this, in other words, this one goes to this one goes to this. Now there's a problem because we need this to be a natural mapping. We need the source of this arrow. If we consider the image of this arrow here, its source has to be the image of the source of the arrow over here. So this guy goes to here. Mm-hmm. So this one, the source is no problem. The problem is the target is no longer to this one. Mm-hmm. So really the only thing that this can map to here, the only thing it can map to over here is what? The final state. Yeah, final state. Yeah. So this is like bad, mm-hmm. Right? Like this is unnatural. Mm-hmm. we're ascribing rules. We need this rule to hold that we're here and we do something here, namely follow this, and then map over what that goes to.
I'm gonna rotate the camera a little bit.
Like this way?
Yeah, yeah.
Okay. And also, do we need the light off?
Yeah, I think so.
Okay. So thank you, Matthew. That's really handy. So if we start here and we do the thing over here, we're doing the thing means following the arrow and then map over. Right? We start here, we follow the arrow, map over. That's this one, right? Or if we map over and follow the arrow here, we have to get to the same point, and we don't. We get to a different point. In one case, we follow the arrow here, map over, we get to here. If we map over and follow the arrow, we get to here. And so it's bad. So the only thing to which this can map, the only thing that is legitimate is if it goes to this one here. Whither it goes, it's this one, right? Okay. It can only go to that. That's the only legitimate homomorphism. And if we tried this in CATLAB, it would show that to us. It would say, nah, you cannot map this into here because it's not a natural.
The CATLAB, there's a function called is naturality, and it will return false.
Yeah, that's right. Is a natural mapping, it'll return false. Or if you ask it for all homomorphisms, it would only give this one. Only this one. Because this is the only one that's consistent. This one is not a consistent picture. It's an inconsistency between how you're handling this. But it does allow a push out of 3 states with 4 states. That's fine around this point, but this point only, which is rather pleasing in my mind. Like it knows the natural rules of the situation. It knows what's natural and what's not, and it only allows you to do what's natural, which is what you want. You don't want to do something that inadvertently is unnatural. Okay. Okay, so let's just continue on finishing up the slides, and we can have more fun with examples here. Let's just try this. Come on. Hey. Okay. Oh, look. Yeah. So this is like bad, illegal. Right? Yeah. Yeah, illegal. Yeah. Yeah, it's this, however, is legitimate. It can go to those places. Yeah, and CATLAB will be able to show. So this is something that many people here are familiar with, but I think it's the first time Jeff has seen it. We use pushouts precisely to merge together stock flow diagrams. So we identify certain things. So this shows what we identify between these 2 stock flow diagrams. Here's one stock flow diagram with a stock S, a stock V, and a stock N, which totals these up, and which has a flow here between S and V. This is another stock flow diagram that is SIR. In other words, this is a vaccine-related one. This is vaccination rate. This is spread of infection one. And here we have two flows between S and I and R. And we're going to take their push out of X and Y over LB, where S is identified in this foot. So S, we're saying identify this and this. In other words, glue these together on S, these X and Y together on S. Consider those the same. We identify S here between them. And N, we identify between them. And this is what we're going to get. We're going to get a stock flow diagram with SIR and a V compartment. In other words, the stock flow diagram with spread of infection and vaccination in it, in a common one. And where N will total up the number of people across all stocks here for this combined model. So this is having a way of composing models, but composing them in ways that doesn't just treat them as totally separate. It merges them together around common points. And this is through a mechanism called structure co-spans, but basically this diagram here is a push-out square. So this is our this is our C down here. This is our A and B, and this is our push-out. And so there should be a little like push-out thing like this here around this thing. This is our push-out. The push-out of X and Y over L sub B. Or just take these together. So S, there's not two S's here, there's just one because it's identified. There's not two N's here, there's just one because we've identified them. And in fact, the link from S to N is also identified. We have a link from S to N here, we have a link from S to N here, and it's the same link from S to N here. So we've stuck these together, and we could do the same thing readily with causal loops. Okay, so I had mentioned this earlier, pushouts, pushouts where C is the initial object, basically have no meaningful information added with S and T, right? This is just what it has to be, and there's no choice in the matter. There's no extra information added about this mapping T or this mapping S as to what is identified in A and B. So here A and B are just coproduct. We could write it like that, coproduct of those two. They're just side by side. We're not identifying anything. It's initial. There's nothing being found inside of B that's also being found inside of A that adds information. It's just the only possible morphism there is. This is gorgeously beautiful, and that's why it's on the scarf. I should wear the scarf as it gets colder. So here, so you tell me, is this a push-out diagram or a pullback diagram?
Both.
It's both. Where is the push-out, the one that we've been discussing? Where's the push-out?
Bottom right.
Bottom right. Where's the pullback? A intersect B. So just like Jeff intuited, this is A union with B, except we've identified the common part that's their intersection. It's not like all the things of A totally distinct from the things of B. That would be the coproduct, right? Remember this Alice's apple, Bob's apple are distinct. Here we're identifying as the same in A and B the things that are in their intersection. Why are these monomorphisms? Like, why is there monomorphism from A intersect B to B? It's just a simple question. It's a subset. It's a subset. This is a subset. This is a subset. This is a subset. This is really incredibly beautiful. Well, I guess if you see it, you'll see it. It's gorgeous. Yeah, maybe I'll just make some closing remarks. So we've been seeing, product and co-product and pullback and push out these past couple lectures. And we also saw equalizers and co-equalizers, right? And I do want to point out that there's a common theme and a common feel to the whole thing here. And I hope this is evident, but if it's not, I want to emphasize it. So products. Do you remember? I mentioned last time, but do you remember what the product is of if we have a category where the objects are sets and the morphisms are inclusions? Do you remember what the product is for that? So in other words, if we have this type of category, in other words, a morphism, what's that? Intersection. Remember that? So it's kind of taking two sets and like finding the subset of them, the restriction of them, to their common point. Do you remember that? Do you remember what it was here, the product? If we had the objects are natural numbers and the morphisms are less than or equal to minimum. Remember that? Do you remember what it was here for Boolean? And this is implication, and arrow is implication. What implies? And remember that? And I want to point out, and this is important for my point, for the perspective I'm trying to convey, and is quite picky in the sense of you're only going to get true if both of the things you take A and B. Under what conditions will that result be true? If A and B are right are true. In other words, if either A or B is not true, you're not going to get true. Right? It's quite picky. It needs some all to be like that, right? And this is very much the flavor also of product, more even in something like set and functions, where if you have the product of two sets A and B, the product of them, if B is empty, it doesn't matter how big A is, it's going to be empty. Right? You might think, well, product has all these combinations. Well, that's true. But if any one of the sets are empty, you're going to get nothing out. It's very restrictive. Remember that? And you may remember that pullback was also quite restrictive. So pullback took product, and if you remember, it restricted it even further. Do you remember that? So to use Eugenia Cheng's example, a brilliant example, right? Here we have shirts and pants, and we could consider all pairs of shirts and pants as the product, but this is matching pairs of shirts and pants, right? It's more picky. It's more a subset of them, right? Or it's a subset of these, right? Here, multiples of 5, multiples of 2. This is a subset of each of those, right? And my point is that these product related ones, or these limits, kind of have this sense of constriction, like the minimum, the intersection, the subset of the product, in the sense of like, if any of the items are non-existent, you won't get anything out. Co-product and co-limits have this sense of more tolerance for diversity. You have like this and next to that, right? And what it does instead, by the way, the equalizer, similarly with equalizer with a sort of pickiness. I don't know if you remember that, but if we had the equalizer, we were taking, do you remember what the equalizer did? It took the subset of X such that what was the case? It's a subset of the elements of X. So here's our equalizer. And it's going to consist of all of the subsets of X. So again, restricting X down to be just those that are what? It's a connoisseur. It demands that what equals what? These are the subset of X for which f of X equals g of X, right? It's sort of being picky. It's restricting down. By contrast, coproduct is actually quite effusive, like coproduct, quite generous, it takes Alice's things and Bob's things and gives you all pairs. If Bob doesn't have anything, you still get Alice's, right? If Alice doesn't have anything, you still get Bob's. And so it has this sense of having more, erring on the side of more things. Do you remember? Let's go through these examples. What was it when we have sets as objects and inclusions as morphisms? Like this is morphism from A to B if set A is a subset of set B, not necessarily just a proper subset, any subset. So what do you remember what coproducts are here? Union, sort of a big tent sort of thing. It takes all of them, right? What do you remember what it was for Boolean? Or, right? It's very tolerant of, if either one is true, it'll be true, right? Do you remember what it was for natural numbers ordered by like less than or equal to? No. Max. It's max. So if any of them are high, it'll be high. But so it has this tolerant feel. But what is it? What gets? So if we consider the co-equalizer, and since we can define, I think the pushout in terms of the co-equalizer, also the pushout. What is it we do? So we consider this or this like next to each other with coproduct. But now we start doing what with like a pushout? We take them next to each other, but we glue them together. We identify some things, right? Right? We consider some things as the same. Same thing. Do you remember the same thing with co-equalizer? So with co-equalizer, we considered, we're not taking subsets of X that have to match this property. That would be equalizer. We're taking Y, and then we are taking equivalence classes of Y, right? If there's any X that maps, I think to one element of Y and to another element of Y, those two things, Y and Y, are considered the same, right? So here we're taking things side by side, but we're considering some things jointly, and that's very much the feel with pushout, right? We're taking some things side by side, and we're identifying some things with pullback, that are mapped to by the same C, right? So we're taking these side by side, but we're identifying these and gluing them together around that. And again, it's very much the co-equalizer feel, but it's still very much a big tent thing. You have A's, you have B's, but then you have some things in common, which you treat as being in common. Hmm? So colimits have this very loose feeling. Now, John Buys has fascinating. John is just awesome in these insights, and this has benefited much from John's insights. But one thing I will say is, like, John talks about this coming out in adjoints as well. When you have adjoints, and that's not something we're talking about much in this course, but you know, I think it's the right adjoint is more restrictive, and the left adjoint is more loose or more liberal. It sort of allows more things in. So you see this with limits, and you see it with colimits, and we're going to see it in big time with sheaves and co-sheaves, because we're going to have pullbacks coming from sheaves. And we're going to have things like for temporal sheaves, they're going to ask for persistence. It needs the thing to be there in each and every time interval for it to be there for the entire time. It's looking at persistence. What things persist all the way through. If it's missing from even one interval, it's not there. It's not persistent. By contrast, co-sheaves, temporal co-sheaves will be looking at accumulation, sort of adding things up, right? Like we're combining some things in, but we're taking pushouts to reflect the fact there might be some overlap. But we're accumulating up, we're glomming together, we're sort of taking more and more things and considering some things the same. This is going to come out in co-sheaves. And so this feel that you may be getting about sort of, remember UJS said last time, you know, like pullbacks of graphs, they're kind of constrictive things, like you can't have a map between XA and XB, or between XA and YB unless there's a map between X and Y on the one hand and A and B on the other. You need it to be in both. And if you don't have it in both, it ain't going to be there in the result. And so you might have a hope that pullbacks are more interesting, but it's very constrictive. It's very picky. But meanwhile, pushouts, very, very accommodating, very, very much allow for freedom and flexibility in mapping things together. Both are super useful, don't get me wrong. But my point is that pushouts of graphs have all these fascinating little cases with them where pullbacks with graphs tend to have this kind of strictures feel associated with them. It's like you're taking the graphs and you're getting something that has some restrictions on it compared to just their product, for example. And even their product, if one of those graphs is empty, for example, you're not going to get anything out. It's picky. You know, it demands something of everything, which has its role, but it just lends itself to a different feel.